developing next-generation research and technology, facilitating connections between AFRL industry and academia, unlocking innovation through a culture of collaboration. This is the AFRL Regional Network Midwest.
Hi, I'm Dr. Hsu from Spectral Energy. Today, I would like to briefly introduce the background and the innovation of the proposed mini-amateur snapshot hyperspectral imaging sensor. AFRL seeks a UV to near-IR hyperspectral imager that can provide a unique 2D snapshot of plasma and the TPS ablative material, temperature, and the reactive species distribution. To achieve this goal, the desired hyperspectral imager must be able to simultaneously record 2D spatial and 1D spectral information. However, the state-of-the-art commercial device can either provide a snapshot high spectral resolutions but with a limited 1D imaging such as the push-pull hyperspectral imager, or snapshot of 2D image but a very low or no spectral resolutions such as RGB-based hyperspectral imager. Right now, no one of the current hyperspectral imaging device can meet AFRL need, and that's why our team proposed hyperspectral imaging sensor based on our special design 2D to 1D fiber converter. It allows to compress 2D spatial and 1D spectral information all into a 2D camera pixels, enabling a snapshot 2D hyperspectral imaging with high spectral resolutions and moderate spatial resolutions. Moreover, the design can be extremely compact and robust to support AFRL TPS material flight test mission.
We are pursuing the development of a hyperspectral imaging payload for reentry environment sensing. We aim to develop a robust and innovative hyperspectral imaging sensor to support AFRL's hypersonic flight testing and technology development efforts. The sensor will provide key information about thermal protection system material performance in reentry spacecraft and further the understanding of the hypersonic plasma environment. This will allow the Air Force to mature new heat shield materials under high Mach flight conditions and provide flight heritage for innovative thermal protection systems.
Since starting this project, we have made progress in identifying the desired spectral information within the detection range of our hyperspectral imager and its sensor design. Our study employs NASA's EQAir simulation tool led by co-PI Captain Rao to calculate the plasma emissions interaction of key gas and the TPS material species during hypersonic flight. After simulating spectral responses, we determine detection range and the key optical component. In the sensor design phase, we use the ZMAX optical design program for developing an efficient, high-fidelity compact sensor. ZMAX is the state-of-the-art optical design tool renowned for its precision in design complex optical system, aiming to enhance signal collection efficiency and minimize image distortion.
After generating CFD flow field solutions of a representative reentry capsule at different trajectory points, we use the flow field data as inputs for the NetAir code to compute the simulated radiance of the plasma sheath. The figure here shows the simulated plasma radiance between 200 and 800 nanometers. As you can see, the system is dominated by molecular emissions of NO and N2 here between 200 and 500 nanometers. Also of note is atomic oxygen, which manifests here at 777 nanometers. We can track the evolution of this emission throughout the descent of the reentry vehicle by simulating the radiance at different trajectory points. The current flow field solutions are limited as they are generated from 5 species CFD models. Running 11 species CFD models with ionization and ablation into account will introduce many more emissions into these computational results, which are sure to manifest during actual flight. For example, the interaction of the plasma with the thermal protection system or TPS materials introduces carbon species into the free stream, which manifest as molecular carbon species such as CN violet and C2 swan shown here. The manifestation of these species and other carbon compounds in the plasma will affect key parameters like the density and the temperature. Capturing emissions like these in high fidelity is key to understanding fundamental interactions between the plasma sheath and the TPS material in hypersonic flight, and this is one of the main objectives of this project. Our team successfully completed the design phase of the fiber-coupled hyperspectral imaging sensor within the first 6 months of this R&D project. The initial work involved determining the design and operating parameters for the sensor. we utilized a simulation tool to compute the radiative emission spectrum from the plasma sheath of a representative reentry vehicle. This simulation was crucial in helping define the sensor's detection range and resolution requirements for hypersonic flight. The alpha version of this compact sensor design, shown here, demonstrates its capability to detect an area exceeding 10 inches with a working distance of 70 inches. In terms of hyperspectral detection, the sensor covers a spectral range from 350 to 900 nanometers with a resolution of approximately 0.5 nanometers. This coverage enables the sensor to effectively capture the emissions from many chemical species of interest in the plasma, which provides valuable insights into the plasma aerothermal chemistry during hypersonic flight. Next, our primary objective is to construct a sensor that is compatible with the space environment and also designed to endure the harsh conditions in the reentry environment. In the next 6-month increment, our focus will shift towards the development of an automated sensor control program. This program will be seamlessly integrated with the control system of the flight vehicle, ensuring efficient and synchronized operations. In the final 6 months of our timeline, we will develop plans for integration of the sensor with an actual flight vehicle and plan a flight experiment for demonstration. This will be dedicated to acquiring re-entry plasma emission data, which is a critical step in validating the capabilities of our sensor. We firmly believe that the comprehensive data obtained during these demonstrations will yield valuable insights into the intricate interaction dynamics between the plasma sheath and the re-entry vehicle heat shield. This knowledge will significantly contribute to our understanding of the high-speed aerothermal environment, marking a significant advancement in our research and development efforts.